So now I want to take a look at Friedel-Crafts acylation. And Friedel-Crafts acylation is also taking a halogen, okay? But now we are adding an acyl group to it. So let's just go back to Friedel-Crafts alkylation. Friedel-Crafts alkylation is when you take a alkyl halide like this, treated with the Lewis acid, and we eventually convert that into our product that looks like this. All right. See how we have an alkyl halide? But now in Friedel-Crafts acylation, we use an acid chloride or an acid bromide. And what that's going to do is going to replace this carbon-chlorine bond once again, just like in this one. Here we replace that bond with that bond right there. So in an acylation, we are just going to replace that just like that. So hopefully you can see the piece that we're adding to the benzene ring is that piece right there. So the mechanism is going to be very similar to the Friedel-Crafts alkylation. It's just generating that general electrophile is going to look a little bit different. Okay? So let's break that down. So like in the previous videos, we have to generate an electrophile for the benzene to attack. Some may argue that that carbonyl-carbon is the electrophile, and your argument is correct. It is an electrophile, but it's not a strong enough electrophile for the benzene to react with it. So we're going to take our acyl chloride here, and we see we have a halogen, and that's going to react with our aluminum. All right. Let's see this color. So we'll come in and attack our aluminum. And what is that step called? That is a coordination. There's our coordination step. And so that's going to give us this piece. Another halogen attached to aluminum, Cl, Cl. What would the formal charges be on this aluminum? That would have to be negative. Chlorine would have to be positive right there. Now we have another step here. And if you watched all the previous videos, what is that step going to be? That would have to be a heterolysis step. And I didn't leave myself enough board space, did I? Well, squeeze it up here. So what the heterolysis step is going to look like is like what we've seen time and time again. This is going to pop off like that. So that's going to give us this piece. Nope, that's no longer there. It's going to look a little weird. Okay. If we number these carbons here so you can see it better. 1, 2, 3. 1, 2, and 3. Right there. And this species right here is resonance stabilized. So it could look like this as well, because we have our 2 lone pairs right there, like that. And so one of those lone pairs could come down to help stabilize that positive charge to give us a species that looks like this. Like that. And so now that is positively charged right there. And that species right there is called an acylium ion. Let's make sure I spell that right. That'll run out of space over there. So that acylium ion is a strong electrophile that is resonance stabilized. All right, so that's what's going to happen. That's the product of the heterolysis step right there. So now we have generated a very good electrophile. Now that's when benzene can now come back into play. All right. So I'll go like this, right there. And when benzene gets into play, let's draw benzene here. Okay, there's our benzene. And if I draw it mechanistically, and I take these pi electrons here and come in and attack that electrophilic carbon, what type of mechanistic step did I just do? What is that called? That would be called the electrophilic addition step. And that's going to generate our product. And I'll draw it down here. Okay, yeah, you can still see it. So that carbon, 1, 2, 3, double bonded O. Just like that. So based off of that number code, you see that's carbon 3, 2, and 1. So but what is still there? There's still a hydrogen. And then there's still this hydrogen there, which is a little cut off. But what's here? That'd be a positive charged carbon right there. You can't see that very well, can you? I'm drawing smaller and smaller. So we have our carbocation right there. So our next step is going to be irreversible. That would be our electrophile elimination. And so we need a base to abstract this proton. So where would our base be? Well, I forgot in this heterolysis step to draw one of those products. We have this piece still here. And so we have aluminum, chlorine, chlorine, and negatively charged aluminum. We will now take that, use one of the aluminum chlorine bonds and use the 2 electrons in this bond. Come in, abstract that proton to restore aromaticity. When I did that, that chlorine taking this hydrogen, that's also going to give us HCl plus our aluminum trichloride. And there's our products. So that is a Friedel-Crafts acylation mechanism. So what I want to do is just compare and contrast the Friedel-Crafts acylation. What does acylation mean? An acyl group is this. I do this little squiggly because it's attached to something that I don't necessarily need you to see. It's just when you attach directly to whatever that thing is, a carbon with a double bonded O and then more carbon coming off of it, that's an acyl group. And so with respect to the benzene ring, It is just a benzene ring, but what have we added to it? That group, and that group we could call a acyl group because it matches the formula here. Double bonded O with a R group. But a Friedel-Crafts alkylation is the situation where you take a benzene and you add an alkyl group to it. Okay. Because in the previous videos that I've done with the Friedel-Crafts alkylation, we tacked on a terbutyl group. And that by definition is a R or just carbon, which is alkyl. So I hope that the names will help remind you of what's going to happen and what reagents you're going to need.